Yo, what is up, guys? Welcome back. Um, yeah, welcome back. Gonna be filming another episode today. I believe this is episode 80. I don't know, 86 or something. Something around there. 86. Yep. We're gonna check out our Pokemon of the day. We got a seal today. Seal Pokemon. Let's do sound. Check out the seal cry. Boop, boop, boop. That's how it sounds. Boop, boop, boop. There we go. What a beautiful sound. Yeah. Let's check out our problem of the day to get us started today. Ooh. It's cold. Interesting. Lowest common ancestor of deepest nodes. Today, given the root binary tree, we return the lowest common ancestor of its deepest nodes. Return the lowest common ancestor of its deepest nodes. So we're given a root here. Given the root of a binary tree, return the lowest common ancestor of its deepest leaves. Okay. So I'm trying to think here kind of how we can do this. I'm trying to think here. Can we use BFS? My initial intuition here, we have looked at this problem before, yes, but I honestly cannot remember anything. But my initial intuition here is that we loop over each node, right? And as we get to a node, if it has the nodes colored in blue are the deepest leaf nodes of the tree. Okay. The deepest leaf node in the tree is 2. The LCA horn node is itself. Okay. Maybe not. I was thinking we could run through BFS and we could keep looking over each node. And we could keep just storing our parent in some other separate node, right? And then once we find our lowest common node, then we can just return our parent. But I don't think that works, because if we have one node, then we don't return the parent, we return itself. So we have different edge cases. Do a post-order traversal. And if both subtrees contain a deepest leaf, you can mark this node as the answer so far. The final node marked will be the correct answer. Okay. So we do a post-order traversal now. A post-order traversal, I believe. We haven't really worked with trees in a while. A post-order traversal would be... Okay, so in order would be left, root, right. Pre-order would be root, left, right. And then post-order, I think, is left, right, root, I believe. Left, right, root. Okay. Why the post-order traversal, though? If we start going left, we... Okay. We did find this problem tough. I know we've attempted it before. We want to do a post-order traversal, which means I believe this would be a recursive approach. Okay, so what I'm going to do here is I'm going to define our recursive approach here. We're going to pass in our node. We might need more. Okay. We define our recursive approach. And then we want to return. Sorry, we want to call our recursive approach here on our root, right? Trying to think here. We get to. Let's first of all implement the post-order approach, right? So if we don't see a node, I believe we return. If we want to do a post-order approach, we will do is equal to DFS dot left right root, then we go DFS dot right, right? Okay, well, if we're going top down here, we would start from here. We keep going left, right? Because we'd be calling this left function. So we keep go left. We'd see a node, we return nothing. And to 6, we check right, return nothing. Then what is our actual function returning? Nothing, right? We want to return something, right? We want to return maybe the node. Return the node. I just really struggle with recursive algorithms. Really struggle to think about it. It's tough to think about it on the spot. DFS node dot left. We get to our 6. I'm just checking. Okay, so we have implemented post-order traversal, but we're going to need our depth, right? Okay, so we're starting at depth 0. Right, we're increasing our depth each time. So to increase our depth, we do depth plus 1. Okay, depth plus 1. Some way of keeping track of the lowest common ancestor, right? So keeping track of the depth. You realize you want to find the lowest common ancestor. Keep track of the depth. Let's get our left depth here. And we get our right depth, right? If not node, right, we want to just return the depth, right? Okay, we get our left depth and our right depth. We want to check, well, if the depth of these are the same, if we're going to somehow check. We have to somehow check, well, is left depth the same as right depth? Because if they're the same, then we would return the lowest common ancestor. Okay, so we're super close. Let's walk forward step by step without writing. Okay. Your DFS returns depth, then tries to return node. That's inconsistent. You need to return both the maximum depth in the current subtree, the LCA candidate for the deepest node. Node is none. Left depth, right depth. Okay, so maybe we check, well, if the left depth is equal to the right depth, then we want to return the node. If left depth is greater than right depth, then we want to do something. Right, but if our node is in the right subtree, so if right depth is greater than left depth, then we need to do something as well. Right. Left depth, right depth, we need to unpack the tuple. Okay, right underscore RCA. Right. Do we return the first node? We will return node.left. Return the left's result. Return node.right. So I'm thinking, I don't know. Left depth node. We return left depth. Mm, 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 mm. Do we need this return statement here? Interesting. So we looped through. We checked. Well, so finishing this code, we do left depth here. We go all the way, right? Okay, get here. Return something here. Call right. Return something here, right? Go back. Go right. Okay. Here. 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 Back. Back. Back to the right side then, right? And then I'm just gonna compare eventually. Well, if left depth is equal to write depth call left, call right. First left call, 5-1. And we're at 6-2, right? Okay. Call left, none 3, returns 3, none. Call right. Return 3-6, but both depths are equal. Then our first right call. Depths are equal. Call left. Turning from 2-2. Left depth 4, left LCA 7, right depth 4, right LCA 7. That's equal, so return 4-2. Current node is the LCA. Returning from 5-1. Left subtree is deeper. Okay, I think I understand. Okay, good problem. I was just a little bit confused with the recursive calls. I understood the post-auto traversal, but I couldn't really like kind of apply like how that worked. You know what I mean? Like I understood the recursion, I understand the recursive steps, but I, didn't realize that we were kind of looking at each step when we were returning the node back. So, but I cleared it up now, so that's good. Anyway, let's jump into another problem today. Again, we want to jump back to our graph problems. Am I liking the graph problems? Probably not really. Max area of an island. We did course schedule yesterday. Let's check out this graph valid tree. Graph valid tree. Oh, it's another premium problem, man. Oh my gosh, dude. Number of connected components in an undirected graph. Let's check out that one. That looks like a good one. Connected components. Bro, why is everything premium, dude? Oh my god. Number of enclaves. Let's check this out. Ooh, a grid problem. I'm a little confused with this problem. You give it an M times N binary matrix grid. Where 0 represents a C cell and 1 represents a LAN cell. Okay. A move consists of walking from one LAN cell to another, 4-directionally LAN cell, or walking off the boundary of the grid. Okay. Walking off the boundary of the grid. A move consists of walking from one LAN cell to another, 4-directionally LAN cell, or walking off the boundary of the grid. Okay. Return the number of LAN cells in grid for which we cannot walk off the boundary of the grid in any number of moves. So we're looking for a LAN cell that I think is surrounded by stuff. This one doesn't count because there's a grid there. So this one here, I believe, would return 2. Okay, we return 0. All ones are either on the boundary or can reach the boundary. Okay. I understand now. So I think we're returning... Okay. I think I understand. Okay, so we're returning the ones that cannot walk off a boundary, right? So we start here, we loop through, right? And we perform BFS on each of these, and we check the distance, right? We check here, here, and here. If this is out of bounds, we don't count it. But if somehow we get through this and it's not, we run the BFS and the BFS doesn't go out of bounds, then we can count these. Maybe we go back to this problem. This is kind of build up one, because we're still studying graphs, so. An 2D grid consists of zeros, ones, water. An island is a maximum four-directionally connected group of zeros. A closed island is an island totally all left, top, right, bottom surrounded by ones. Return the number of closed islands. Given a 2D grid that consists of zeros and ones. 0 is land, 1 is water. An island is a maximal four-directionally connected group of zeros. An island is a maximal four-directionally connected group of zeros. Okay. And a closed island is an island totally all left, top, right, bottom surrounded by ones. This is an island here. Then we have an island here. I'm a little confused by this diagram here. Okay, I prefer the other problem better. We're going to go back to the other problem. This one's a little confusing. I understood the other one. No, what was it called, bro? Number of enclaves. Okay, here we go. A move consists of walking from one land cell to another, four-directionally land cell, or walking off the boundary of the grid. Return the number of islands in grid for which we cannot walk off the boundary off the grid in any number of the moves. Okay, 1. Let's return 0. Okay. So firstly, we need to create our full row in grid in okay, right, for okay, well, let's just do our rows is equal to the length of grid and our cols is equal to the length of the grid indexed at 0, right? We do for row in rows and for col in cols. Okay. We want to print. Let's print our row col. Let's print our row col. See what we get here. Oh, we forgot to reference our grid. Ah, I hate this, bro. For row in range, no, we need to add in range rows. In range cols. Okay, so we get 0, 0, 0, 0 4 zeros, we get a 1. We get a 0, we get a 1, 0, 0, blah, blah, blah. Okay, right? So we're looping through, right? And first of all, we need to check, well, if the grid row col is equal to 1, right? And not in visited, right? So we want to create our visited array here. So we create a visited, and we make that equal to a set, okay? If it's equal to 1, and we haven't visited yet, then we know this is a new island, right? So we've got to this element here. We know that it's a new island, and now we need to run some sort of BFS function, right? So now we need to, from collections, re-import the DQ, right? We're at this point. We want to check, well, we need to create, I think, like a directions array of some sort. Directions, right? We pass in, well, okay, what would be left, right? So left would be, what would left be? I think it would be, this is really gonna fuck me up. Hang on. So I think, let me draw this. Okay. So if we were to compare our left and right, if we wanted to move from here and we wanted to check the value over here, we'd have to move, these are rows. I believe we'd have to move our column by 1. So I think it would be 0, -1. To move right, it would be 0, 1. And then to move up, we'd have to mess with the columns. We'd be -1, 0. And to move down, we would increase by 1, right? Because we'd be increasing our value here by 1. So we would increase by 1. And this would be a left, right, down, up. Okay. So, right, we've checked this value and it's not in visited, right? Well, we want to check it's not in visited. We want to check, well, we want to check its neighbors, right? So we would have to, shit, if I do another for loop, isn't that going to be like an n-cubed solution? How do we do it in the other one? Let's check our OG rotting oranges example, how we did this, because okay, so first of all, we put all the rotten oranges in a queue. Okay. Okay. So my bad. So to avoid an n-cube solution here, we need to put all these oranges in a queue, right? So we need to check, well, if they're equal to 1, then we put them in the queue. So we would do, well, queue.append. We'd append our grid. We'd go row, we go col. Our grid, row col, right? That's what we did here. I guess we can row col. Row and our col. That's really all we need, right? We don't need anything else. We just need to append our row and our column, right? So we check they're equal to 1. I think that's what we need to do, right? So here, really what we're doing is we are building our queue, okay? Then in our next part here, we want to run BFS on the directions, right? So we have our hashtag 1, we have our hashtag 2, okay? We come here, now we want to do it, we have a tuple here, right? So we want to do, well, while queue, okay? We want to call a for loop here on our cur row, okay? Cur row, cur call in directions, okay? We need to obviously pop first, so we do our queue dot let's do like our, we need our cur row, our cur call is equal to queue dot pop left. Alright, so we pop here, then we check, okay, how can we loop here? Well, actually, pause. I'm kind of liking the vibes here, man. We got a thunderstorm outside, you know, we're running some code, we're like, you know, kind of balling here, man. This is kind of some nice vibes. Maybe I get on a little candle back here or something, you know, get the vibes going a little bit. Anyway, continue, right? So we see this. We see the cur row, we see the cur column in directions, okay? What do we want to do now? We've popped them. Now we want to compare, well, we want to create our new row, okay, is equal to, well, actually, let's do, we want to pass in our new row, call our end row, end call, okay? Let's refer to this asccall. This is our current, right? That's what we're referring to. Then we call it our new row, right? We say new row is equal to, well, current row plus end row. And our new call is equal to current row plus new call. And I believe you should see that in our rotten oranges problem over here. Yes, looks good. Okay, so now what we need to do is we need to check. So we create an if statement and we check, well, is it in bounds, right? Is our 0 is it in bounds, right? So we need to check, okay, well, 0 less than or equal to new row, right? Because technically it can be 0, right? So that's why I have it equal to 0. It can be 0, right? Or it's greater than our rows, right? We don't want it to be equal to because it can't be equal to rows because technically it's 1 indexed, right? And our array is 0 in this case, right? So we check if 0 is less than or equal to new row is less than rows. And so we're checking our bounds here. So let's put a comment here. We're checking our bounds. Okay. And 0 is less than or equal to new call. And is less than or equal to calls, right? That's what we got here. Okay, so we know that this is in bounds, right? If statement goes through, it is in bounds. Okay. When we were in bounds, right? If it's in bounds and it's equal to 1, right? Because we need to make sure it's equal to 1, right? We need to make sure it's an island, right? If it's an island that it's in bounds, and we want to run this again in our queue, right? So if it is, how do we check if it's 1? And let's do grid new row and new call is equal to 1 and Why do we have a... Why is it orange here? Okay, never mind. Okay, and... want to make sure that it's not visited, right? Okay, and... Okay, I'm going to make sure it's not visited. Do we have to check that it's not visited? I think we do need to check if it's not visited. Because we could be here. We check here. We see this is a 1, right? We pass it in. Then we could go here again and we could see that this is a 1, so it could go back, right? So I think we do need to check if it's inside of our set. So we have to check, well, and let's do like new row, new call, not in visited. That is a really long if statement, bro. Oh my gosh. Okay, right? Okay, make that a little bigger. Not in visited. We need our parenthesis here, right? Okay, if we see this node, then we want to add this node to our queue. So queue.append, new row, new call. And then we want to add visited.add. Okay, we want to add new row, new call. I might have to look this up because I'm not sure if this here is working properly, but I hope you can understand my logic for at this point, right? So okay. So we're at this point. We've appended, okay? So we're appending our 1s, right? I guess now we need to check, well, so we're checking if it's inbounds and it's not equal to 1, right? So maybe the better way would be to check, well, maybe it's out of bounds, right? If we check if it's out of bounds, no. Okay, we add to visited, right? But when do we know that we can actually count this as an island, right? That would be at the... No, because we're popping each element, we're appending a new queue. So how would we be able to keep check that this is one whole island here? I'm not sure. I'm not sure how we do it because we're technically popping from our queue each time, right? Let's ask from here because I'm not sure. Okay, so I have a good start, right? I didn't even make our DQ. Whoops, that is awkward. Let's make our Q is equal to DQ, right? We did that. We're building our Q here. Add all the boundary land cells to the Q. Add all boundary land cells to the Q. Ah, that is very, very smart. Ah. That is really smart, dude. So, what GPT just told me, I think, if I'm not mistaken, we're adding all boundary land cells to the queue. So we add all these here. So row is equal to 0, or row is equal to rows minus 1, or col is equal to 0, or col is equal to cols minus 1. And grid is equal to 1. We add it and we visit it. We perform BFS to mark all reachable land cells. Okay, so that's so interesting, right? So we mark the boundary ones. We perform BFS, see if we can reach any of these other ones. And then our final loop here would check what is left. So what ones, we loop through this again, and we check what ones are visited, what ones are not visited, right? And then we count those and return that count. That is a really interesting way to think about this problem. I really, really did not think about that. That is really smart. Okay, so now to check this, we have to fix this if statement here, right? And we're gonna have to fix this if statement here as well. Fix if, right? So we can keep this code, but we have to check here. Well, okay. Well, we need an if statement here, and we need to check. Well, okay. So what would be a boundary cell, right? So if row is equal to 0, right? So if row is equal to 0, or row is equal to rows minus 1, and I believe that indicates this one down here, okay? Or rows is equal to rows minus 1, okay? I think it's all the whole way, right? Okay, yeah. Or if col is equal to 0, right? So if we're looking at this column here is equal to 0, or cols is equal to cols minus 1, which I believe would perform this one here, yes. So we want to check all these, okay. Then we want to check, well, we need to make sure it's equal to 1. So let's do and grid row col is equal to 1. Then we put it inside of the queue, right? Inside of the queue here. And then we run BFS on the directions. Okay. So q.append row col. Okay. We run BFS on the directions. Okay. So now we're checking, okay. Now we have to see what we can get to, right? So now we just have to typically just check if it's in bounds, right? So we would do, well, is 0 less than or equal to new row, and is less than or equal to, my dad's calling me. 0 is less than or equal to, so we're at 0. I'm getting distracted from this phone call, man. So less than or equal to new row. We're checking the length of our row. My dad just spam calls me, bro. Oh. Zero is less than or equal to new row is... Oh, finally, dude. Oh my... Less than or equal to new row. But is... What is less than the length of rows? I believe. Yes. Okay. And 0 is less than or equal to new col, which is less than or equal to the length of cols. I guess we can just do cols, not the length. We would do just rows. We would do cols. Okay. And we need to check if the grid, new col, sorry, new row, new col is equal to 1. We would append, right? We mark it as visited. Here we also need to mark it as visited. Visited.add. Do row col. Okay, then we do visited.add new row, new col. Okay. So I believe that's good there, right? So we check that. And I believe after we're done with this queue, we have to count remaining ones not in the queue. Remaining not visited, right? The way we do that, we would do, well, I guess we'd start our iteration again. Well, for rows, for row in range rows, for col in range cols, we want to check, well, if reference, what is it, our grid, if grid row col not in visited, then we simply just want to increment our count. We need a count variable right here, starting at 0, then we count plus or equal to 1, and then we'd want to return, well, our count. Let's give it a run. Looks like we're stuck in some sort of infinite loop here. Memory limit exceeded. Why are we getting a memory limit exceeded though? I don't know why we were getting a memory limit exceeded. Oh my god. And row, sorry, and row col not in visited. Then we count. I think that should be good. Oh no, we got some sort of while loop error, dude. Oh my gosh, man. Rows cols. If grid row, oh my gosh, is equal to 1. We're getting a memory limit exceeded, so I feel like it's something to do with some sort of... Oh. Less than rows, less than cols. Okay, we don't want it to be equal to it. Okay. And not in visited. Right, I think that's what's giving us the while loop. We didn't check if it's in visited, so, and not, and new row, new col, not in visited. I believe that's what's calling us the while loop. Okay. So at least we're getting somewhere, is that? Yeah. we append. Check C row, C call. Okay. What are we getting here? We're getting output 2, expected output 1. I'm not sure what our error is here. I believe this should work. What is our error? It's gonna be something stupid, I guarantee you it. Okay, we got rows here. Rows -1. I think that's it. No? If row is equal to 0, or row is equal to rows -1, or col is equal to 0, or I believe this would be col is equal to cols -1, and then we check row col. Okay. Pro. Rows equal to 0, rows equal to rows -1, cols equal to 0, col is equal to cols. Mgrid row col is equal to 1. What? Did I do something wrong again? I'm gonna copy it right here. I don't know. The logic seems right. Oh, did I mess up my direction? -1. Zero, -1, 0, 1. -1, 0. The comment is incorrect. That's what it's telling me. Okay, yeah, I realized that. Okay, so this is up. This is down. Okay, well that doesn't really help anything, but the actual issue lies here. You meant... Oh my gosh. C col. There we go. Interesting solution. Okay. Okay, let's take a look at this other problem. In my opinion, this question should be removed. I felt like that was a good question. Let's actually, I'm going to share my solution with the world. Okay, I believe our time complexity here would be our intuition. PFS, baby. loop through, interview solution, BFS. BFS. I'm gonna put some clickbait titles here, bro. Gotta get those clickbait titles in. They get like the rocket emoji, bro. Let's get that rocket emoji. Get the rocket emoji, bro. Throw it in there. Yeah, that's like a clickbait title right there, bro. We got our time complexity here. I believe it's O of vertices plus, no, O of n squared, and, no. O of m times n. O of m times n. Okay, loop through boundary ones. Then apply BFS to those islands. Hashtag 1. Loop through boundary islands. Let's put in brackets ones. 2. We apply BFS to boundary islands. 3. We loop through rows and cols and check which ones have not been visited yet and increment. Okay, that looks good. Clickbait solution. I'll give myself an upload again. Cool. That was a good problem. Let's take a look. Let's check out that profile photo, baby. Let's go. Okay. Let's take a look at some more graph problems. See how long we've been going for here. We're going for an hour and 15. Let's go here. We into this one, redundant connection. Maybe we'll check out this one. Next, let's check out that one, redundant connection. Okay. Okay, so in this problem, a tree is an undirected graph that is connected and has no cycles. Isn't this a cycle? You're given a graph that started as a tree with n nodes labeled from 1 to n, with one additional edge added. The edge has 2 different vertices chosen from 1 to n, and was not an edge that already existed. The graph is represented as an array of edges of length n, where edges I is equal to a1, b1 indicates that there is an edge between nodes a1 and b1 in the graph. Okay. Return an edge that can be removed so that the resulting graph is a tree of n nodes. If there are multiple answers, return the answer that occurs last in the input. Okay, so in this problem, a tree is an undirected graph that is connected and has no cycle. So pretty much I feel like we need to remove the edge that forms a cycle. But what edge specifically? We could remove this edge here and it would still work, right? Like, we want to end with one additional edge added. The added edge has two different vertices chosen from 1 to n and was not an edge that already existed. The graph is represented as an array of edges of length n, where edges I is equal to a1, b1 indicates that there is an edge between a1 and b1 in the graph. Return an edge that can be removed so that the resulting graph is a tree of n nodes. I understand the problem, but I'm not sure how we can isolate the edge that we want to remove. What algorithm we can use in order to isolate that edge. And I'm getting kind of hungry too, bro. Low key, like, okay. At least I know that the first thing we need to do is we need to build an adjacent. Man, what is it called? Adjacency list? Yeah, adjacency list, right? So let's do that really quick. Let's develop our adjacency list, right? Because I believe we're gonna have to figure out a cycle. If there are multiple answers, return the answer that occurs last in the input. Okay. Return an edge that can be removed so that the resulting graph is a tree of n nodes. If there are multiple answers, return the answer that occurs last in the input. Okay. So I believe I'm thinking this problem, we just simply remove the edge that makes it a cycle, right? So we're going to need multiple things here, right? We have a cycle. To identify the cycle, the way we identify the cycle is we create a visited set, right? We create a visited set. We create a graph, right? And we want to call adjacency list, right? And we want to pass in our edges, okay? Right? So we make that. Let's make our graph here, right? So we make our def adjacency list. We want to pass in our edges, right? So let's call this our graph, okay? Let's just call this edges, whatever, right? Okay, we want to form a graph, right? So we make graph is equal to, right, this. Create our graph. Okay, now how do we want to put in our edges? Well, since it's an undirected graph, we need to, when we loop through, our first value is the actual node that we're at. Our second value is our destination, right? But we need to add in both, right? Because it's a undirected graph, so they can go both ways, right? So I believe we can make a let's do for edge in edges, right? We want to do, well, we want to pop our this AB is equal to edges. I guess we make graph A is equal to B. Graph B is equal to A. Oh, we need a dot append A, dot append B, right? Since it's undirected graph, we would append both. Okay, then let's print our graph. Wrong. You're unpacking the full list again. This will throw key error if not in a graph. Oh. Whoops. Okay, so we need AB is equal to edge, right? Okay. We need to check, well, if A not in graph, got this part, we need to actually build the list. If A is not in the graph, then graph A is equal to an empty list. And we check, well, if B is not in the graph, we form our adjacency list, right? Is equal to this. Okay. Graph A, graph B. Okay. And yeah, we want to return our graph, right? I mean, that's pretty simple. We return our graph. It's pouring outside, man. Okay. Let's return our graph. Let's print our graph, right? I think this means that we have to move this method on top of this graph, but I just want to make sure because I'm actually not 100% sure. I always get this error and I always just move it on top. Why this error? Because in Python, you cannot call a function before it's defined. That's what I thought. Okay. Let's move this really quick. Okay, so let's move this up here. Right. We get our adjacency list. We print our graph. Okay. 2, 3, 1, 3, 3, 1, 2. Okay. So I believe here the approach here that we want to do is we want to do a DFS approach, right? And the reason why we want to do a DFS approach is, well, if we're exploring using BFS, we're not going to find a cycle, right? We need to explore one way like this, right? Instead of, you know, breadth first, right? So that's why I think we should use a DFS here. Okay. So we have our set, right? We have our graph now. Now we want to check, well, let me check something. Okay, right. So what do we want to do here? We want to probably call our DFS function, right? So, but let's think about this for a second. How do we actually want to know that we are going to return something, right? Well, if our edges, right, we have our edges here. If we find an edge, I feel like instead of returning false, if we're added vertice that already exists, we just return the edge, right? And then we pretty much delete that edge from our hash map, right? Because what are we returning here? We're returning a list. So 1, 2, 2, 3, 3, 4, 1, 4. Okay, we just want to return the edge that we're deleting, right? We find that edge that connects and makes the connected component, and we delete that edge, right? The way we want to do that is obviously a DFS function, right? So we want to pass DFS, and we want to pass in our first node, right? So we would pass in, I guess, shit, how would we do this? we would pass in, well, what would we pass in? We pass in our graph, our current node. Oh, shit, man. How do we pass in our... Let me look at this. Called DFS. We're going to pass in our graph, pass in our node, pass in our visitor array, right? Okay. We want to, let's make room for our DFS function here. Okay. So we create our DFS function. Def DFS, we want to pass in our graph, we pass in our node, we pass in our visited, right? Let's check, well, if node in visited, right? What do we want to do, right? If our node is in visited, what do we want to do? Do we just return nothing? I don't know. Alright, we're going to get that. I guess we don't really have to loop through each node. I guess we can just simply pass in our first node, right? Is that crazy to say? Right, we would simply just return graph 0, right? Because we're always going to have a connected component. This graph 0 reference first key in hashmap in Python. Okay, so how would we pass in our first element here, bro? Given a graph that's an label from 1 to n. Okay, so I guess let's just start from 1. Okay. If node in visited, what do we want to return? Well, we return probably nothing, right? If the node's in visited. If node I guess for neighbor in graph, no, okay, we want to call, well, I guess we can just like return false, right? if DFS node, okay, we pass in our node. If DFS graph neighbor visited equal to false. False, then we want to if it's if node in visited, we return false. Okay, because it's visited, right? But if we technically go here, let's say we had this graph, we start at 1. We would go through this. We do for neighboring graph node, right? So we append its neighbor. So the first one would be 3, right? Then we'd append 2. Okay, then we go back to 1. We call 1 and see it's false. Okay. Return false back here. I don't think we should be using Boolean, man. Node and visited. Let's return node. Okay. So we get here, right? Return the node. If the node is in visited, we return that node. Okay. And then we would return node 2 is equal to DFS that we would return our node 2, which would be 1, and we return the actual node. So we return node 2. This is definitely wrong. Definitely wrong. I guess we can just return this function, right? Redundant connection. Union find data structure. Keep going, champ. Every engineer with 6 figure salary was in your place someday. This is tough, bro. Does Leetcode have a video on this, dude? I think he does. Let's take a look at the video, because I'm not sure.
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem, redundant connection. We've actually already made a video for this one before, but I think I could make it a little bit better. The idea here is that we're given an undirected graph, so every single edge, for example this one, is always going to go in both directions. And they tell us that actually the graph that we're given does not have any cycles, but we introduce one additional edge, and this edge is not a duplicate. It did not already exist. And also, it's not like going to be a self loop. They tell us that by saying that it has two different vertices attached to it. And then they specifically tell us that we want to return the edge that can now be removed from the new graph, such that the resulting graph is now going to be a tree. So just to quickly summarize, they originally said that they gave us a tree. Then they added one more edge, and now the graph is no longer a tree, but after we can identify the edge that can be removed, then we can end up with a tree once again. And it might be possible that there are actually multiple edges that could be removed, and so if that's the case, they tell us that among all of the edges, we would return the last one. So this problem has a lot to do with graph theory. That's why I think this is actually a fantastic problem, because they intentionally word the problem in such a way that you need to know certain things about graph theory. And I'll try to cover those as best I can in this video, but also if you just want to learn more about these things in general, you might be interested in the DSA for beginners or the advanced algorithms courses. So the main facts about a tree are that it is generally connected and it does not have cycles. So what they're telling us is that they originally gave us a graph that was connected and did not have cycles. Then they introduced one additional edge. In this example, I guess that edge was this one, 2, 3, and now the graph is no longer a tree. And it makes sense. If you got rid of this edge, we would have a tree. You could draw it this way. I guess it would probably make more sense. You put like the 3 over here and the 2 over here. Now it probably looks like a tree to you. But keep in mind that for a graph like this one over here, I guess the edge that we are removing is this one, 1, 4, and this might not look like a tree, but if you were to rotate it and redraw it, it might look something like this, where you have a 2 connected to the 3 and the 1, the 3 is connected to the 4, and 1 is connected to 5. So when you draw it this way, it kind of looks more like a tree. It doesn't necessarily have to be a binary tree. We could have a graph that looks like this. That's also considered a tree. So just keep that in mind. So now it's easier to interpret the problem. When they tell us that we want to remove an edge from the graph to make it into a tree, now we kind of know what we're looking for. We want to remove an edge so that we eliminate any cycle that is in the graph, because we do not want to have cycles. So knowing that, when you look at this first example, it's actually possible to remove this edge and then we end up with a tree. And we could also remove this edge and then we also end up with a tree. We could also remove this edge and we also end up with a tree. So why is the solution 2, 3? Well, that just happens to be the last edge in this list. When we look at this problem, we can identify the cycle pretty easily just by looking at the graph. We see that this is the cycle here. So probably we could remove this edge, or this edge, or this edge, or this edge to eliminate the cycle. We can't really eliminate this one because it's not really a part of the cycle, and then we would end up with a disconnected graph anyway, so that's not going to help us. So now among these 4 edges, which one should we eliminate? Probably the one that shows up last. So I guess these are the first 4 edges, these 4, and the last one is 1, 4, so that's the one we eliminate. These are the edges that are a part of the cycle. We eliminate the last one. That's what we return. So now this problem has become a cycle detection problem. We just have to detect the cycle, or at the very least, identify all of the edges that belong to the cycle in the graph, and there's guaranteed to be a cycle, so don't even worry about that. There's guaranteed to be a cycle based on the problem description. So if you were to identify that these are the edges belonging to the cycle, then one thing you could probably do to solve the problem is just iterate over the input list in reverse order and just check, is this one a part of the cycle? Well, it's not. And then you could go to the next one. Is this one a part of the cycle? Well, yes, it is, because maybe we threw those edges into some kind of data structure, like a hash set. That is a perfectly valid solution. And you can see the code for that solution directly on Leetcode.io. If you are interested, it should be available in most languages, so probably your language of choice. But I want to take advantage of this problem because there's actually a more natural solution to this problem. It involves a relatively advanced data structure called the disjoint set, or I prefer to call it just union find, because union find can also be used to detect cycles. I'm not going to go super in depth into exactly what this data structure is. We will be implementing it in the coding part of this problem. If you do want to learn this data structure more in depth, you could consider checking out the Advanced Algorithms course on Leetcode.io. It has a video, practice problems, as well as this article and a bunch of animations and things to make it easier for you to learn, code snippets in most languages, but you definitely don't have to. So if this is interesting to you, you can consider it, but anyways. So union find in the context of this problem is what I'm going to be going over now. The general idea behind union find, I guess I will use this second example to illustrate it. We start out with a bunch of individual nodes. So in this problem, they tell us that we are given nodes numbered from 1 to n. You might be wondering, well, what exactly is n? They don't even tell us how many nodes that we're given. That's actually a part of graph theory. If we started out with a tree, that means we had some kind of connected graph without any cycles. If that's the case, I can tell you that if we had n nodes, we must have had exactly n minus 1 edges. Because you can see that if now I were to introduce one more edge into this graph, assuming we cannot have duplicates, it's definitely going to result in a cycle like this one. And that's always going to be the case. This is just a relatively simple fact of graph theory. And so thus, if by introducing one more edge into the graph, we added a cycle, we can guarantee that the number of edges is exactly equal to the number of nodes. So it's not a coincidence that in this example, we have 5 nodes and we also have exactly 5 edges, because we're guaranteed that there's only one cycle in the graph. And before we added a edge, there was not any cycle in the connected graph. If we were to add one more edge, that could cause problems, because then we might end up with multiple cycles, and that is not what we have to deal with in this problem. We do not have multiple cycles. So now that I've convinced you that we have exactly n edges and n nodes, now we know what n happens to be. In this problem, it's going to be 5, so we can start out with 5 individual nodes like this. This is kind of how the union find algorithm works. So I will draw the 5th one down here. So what union find will do is it will take 2 components and basically union them together by connecting them via an edge. So the way we can use that algorithm to help us solve the problem, I'll just briefly do a dry run right now. We're going to go edge by edge, and we are going to keep connecting the 2 nodes that the edge belongs to. So for 1, 2, we would connect 1 and 2 together. For 2, 3, we connect 2 and 3 together. For 3, 4, do the same thing, just connect them together. And now that we want to connect 1 and 4, sure, we can do that. We can introduce an edge just like this. But the great thing about union find is that it can actually be used to tell us that this edge that we have introduced, we have actually not connected two separate components. In other words, this can tell us that 1 and 4 already belonged to the exact same component even before we added this edge over here. We didn't need this edge. 1 and 4 were already connected. That's what union find can do for us. And so now you tell me, if that's what union find can do, how can we use it to solve this problem? Well, what that means to me is that 1 and 4 were already connected. There was already a path from 1 to 4, and now we introduced a brand new edge. And given that the edges are undirected, we have introduced a cycle. We have just finished the cycle. This is a cycle. So now you tell me. We already knew this was a cycle detection problem, but we wanted to return the last edge in the input that belonged to that cycle. So what should we do now? Well, by definition, if we just completed the cycle, the edge that we just visited was the last edge in the input that belonged to the cycle. So that's the edge that we can return. So as soon as union find tells us that we have connected two nodes that were already connected, that's the edge that we want to return. So this is how I'm going to be solving the problem. I'm going to briefly talk about how union find works, like as an algorithm. These are the nodes that we start out with. So what we do edge by edge is say, okay, 1 and 2, we want to connect them. So what we say is one node is going to be the parent of the other node. So in this example, we could say 2 has a parent of 1. All of the rest of these technically have a parent of themselves. So they kind of do that. And then we say, okay, 2, 3, let's connect 2 and 3. The way the algorithm works is we will go to 3 and find the parent of 3. Well, 3's parent is itself. We will go to 2. We will traverse up the tree to find the parent of it, the root parent, which in this example is 1, and then we will connect the smaller component to the bigger component. So in this example, rather than doing something like this, where we connect 1 to 3, this would be inefficient because look, it's kind of like a linked list. It's going to be long to traverse. We would rather have a graph that looks like this, where 3 is the child of 1. And now we will add 3 and 4, connect 3 and 4 together. So since 4 is smaller, I guess you could do something like this. You could have 4 as the child of 3, but remember how I said we want the root parent of each component. The root parent of 4 is itself, but the root parent of 3 actually is 1. And the reason we want to find the root parent is because then we can do something a bit more efficient and take 4 and connect it directly to 1. You can see how this tree is a bit more flat than the previous one. We want the height of this tree to be as small as possible. And this specifically is called path compression. And the other thing I was talking about is called union by rank. And these things are covered pretty in depth in the advanced algorithms course. And it's not like super trivial to cover this. And I also won't be covering the time complexity in depth, but I will tell you that given that we are doing path compression and union by rank, each of these operations is going to be relatively efficient. Going up the tree is going to be almost proportional to constant time. It's a mathematical function that I won't go into, but practically speaking, it is a constant time operation. But anyways, to now finish up this example, now we will be connecting 1 and 4. And so if you remember, for 4, we want to find the root component. It happens to be a 1, the root node, sorry. And then for 1, we want to find the root node. It happens to be 1, because for 1, it's going to be self-looping. And so now, that's how we detect the cycle. We find that 1 and 4 already belong to the same component. They have the same root. And thus, this edge will introduce the cycle, so this edge is the one that we want to return. So now I'm going to code it up to briefly discuss the time complexity. Since we're going to be going edge by edge in the input, and that's going to be proportional to the number of nodes, you could say that the time complexity is the number of vertices plus the number of edges, but these will be roughly equal, so I think you could just have one of these terms as well, and that would be fine. To be a bit more technically correct, you could say that you're multiplying these by the function I was talking about, but that one is practically constant, so it doesn't really matter. So let me clear this, and a couple of things that I didn't really talk about in the drawing explanation, just because these are just implementation details of union find, is that we maintain the parent of every single node like this. So we want to have an array that's like of size n, where n in this case, like I said, is going to be the number of edges, so like that. Now technically we want the index of this to be a node, so let's say the ith a node will map to its parent. We know that the nodes that we have are actually numbered from 1 through n, so we really want to skip 0, and we can do that pretty easily. So I'm going to actually implement this with list comprehension, a feature of Python. If you want to learn more about that, you can check out my Python for Coding Interviews course if you're interested. But it's just like this. So for I in range n plus 1. So for every node I, initially its parent is going to be itself. So that's what I'm doing here. This should just create an array that looks something like this: 0, 1, 2, 3, 4, 5. I also want to maintain the rank or size of each connected component. Initially, we could just say it's going to be 1. So this one is a bit more simple. We can just initialize an array of size n plus 1, where all the values are 1. Now there's two main functions to implement with union find: the find function and the union function. That one's a bit more complicated. It takes two nodes. I'll call them n1 and n2. And let's just assume that we had these two functions implemented. And let's say this function will return true if these were not already connected. Otherwise, in this function, we can know that they were already connected by getting the parent of each. That's what the find function is going to do. So I'm going to assume it just works. And then I'll do this: find the parent of n1 and find the parent of n2, the root parent. That'll give me p1 and p2. And if p1 is equal to p2, I'm actually just going to skip the union operation and just return false. I guess I could have completed the union operation as well, but in this problem, we don't really need to. So technically, this isn't a correct implementation of union find, but it works in the context of this problem. So I have my return false and I have my return true. So assuming that these two are fully working, this is how I could finish the problem. I could go edge by edge and unpack the two nodes within each edge, and then I could do this: union them together. And if this returns false, if not the return value of this, then I'm going to return this edge. This was the edge that was redundant. So that's pretty much it. And now to actually implement these two functions, this one isn't too bad. We could do it iteratively, but doing it recursively is a bit nicer, because we can do something like this. We can check if n is already equal to its own parent, then we can stop. Then we can just return itself. Or you could write it this way as well: parent of itself. Otherwise, we want to find the parent of itself. So we can pass in its parent and just keep going up the chain, like recursively. And then the return value of this should be the root parent. And so I want to set the parent of the current node to be that. So this path compression, going up the chain, it will set every single node that we encounter, and it'll change the parent of each node to be the root node. And then from here, we can just return the same thing that we were returning up here. One little way to condense this piece of code is to see that this is duplicated down here. So we could actually change this to a not, and then within that function, or in that if statement, we could move the function call there. And if this doesn't execute, we'll end up returning the parent anyway. And if it does execute, then we'll return the parent. That's why I'm not changing this to be return n. I want it to be return parent of n. But that's just a minor change. You could leave it the other way as well. Now, to finish up the union function, we want to perform a union by rank. So what we want to say is if the rank of P1, for example, is greater than the rank of P2, then we want P2 to be a child of P1. So we could say the parent of P2 is going to be P1. Otherwise, we do the opposite. Parent of P1 can be set to P2. We also then want to update the ranks accordingly. So if I took P2 and it became a child of P1, then the rank of P1 just increased by whatever the rank of P2 happened to be, and vice versa down here. So I'd move this and change that to P2, and this to P1. So this is the entire code. I'll go ahead and run it. You can see here it works, and I promise you that it is pretty efficient. If you found this helpful, check out neetcode.io for a lot more. Thanks for watching, and I'll see you soon. The entire code.
Okay, that was a little confusing. So I think what I'm going to do is I'm going to implement the DFS solution. So it looks like here, instead of using an adjacent list, we actually use a okay, we can keep this, right? Oh my god, what the hell did I just do? Okay, let's just implement it again, right? Oh my god, dude. Oh no. Okay. So we implement our graph. We have our graph. So our DFS function is gonna have to move. Okay, we can get rid of this. We can get rid of this, right? So our DFS function has to go first. Okay. Okay, we want to make our graph. Okay, our graph is equal to this, right? Do for edge in edges. Okay. We want to check, well, AB is equal to edge, right? Okay, we want to initialize our visited set. Visited is equal to set. Okay. Why are we doing that though? I don't know. A in graph and B in graph. And DFS graph A, B visited. Then we return that edge. Okay, this is where we return the edge. Otherwise, A not in graph. Okay, we want to create that, right? If B not in graph, then we want to create that. Graph B is equal to that. Graph A. Oh my god, graph A dot append B. Graph B dot append A. Sorry. Yeah, that's right. Graph B dot append A. Okay, we can return empty list. Right, if I believe that is if there's no edges, right? If we don't return something, right? So now we implement our DFS function. It's a tough part. What do we do here, right? So we check, well, if current is equal to target, we return true, right? That's a base case, right? Because if it's equal to target, current is equal to target. Okay, we return true. Then we add visitor.add, we add current, right? And for neighbor in graph.get current, if neighbor not in visited, and if DFS graph neighbor target visited, we return true. Otherwise, we return false. And the out of 4. Interesting. Okay, right. We loop through for A, B, and edges. We check visit is equal to set. If A and B in the graph and DFS our graph A, B visited, we return that edge, okay? If not, we add A. If A is not a graph, we add A. If B is not a graph, we add B, right? So if we go through here, right, we check 1, 2 first, right? Well, A is not in there, right? Because we initialize an empty set, so we make A is equal to 2 and 2 is equal to 1, right? And then we go to the next one, right? We check, well, if A in graph, which it is, and B in graph, B is not in the graph, then we check, well, if A not in graph, we append A. If B not in graph B, we append 1, right? And graph A dot append B, graph A dot append A. Okay, so then we have 2, 3 here, right? This is where we do the DFS here, right? So we check, well, we go in here, well, 2 is in there and 3 is in there, and we call DFS on it, right? We come up here and we check, well, if current is equal to target, we return true. Well, it's not, right? For neighbor in graph.get, right? Our A is first, right? So 2. Look in 2, we see 1, right? For neighbor in graph.get, current or empty string. If neighbor not in visited, then we call the DFS on it. Initialize the graph, right? Fine. Okay. Let's edge 1, 2, AB. Since neither one is on the graph yet, they append. Okay, now the graph looks like this. Yep. 1, 3. Since 1 is already in the graph, but 3 is not, we add 3. 2, 3, 3, 1. Process the third edge, 2, 3. We see 2 3s in there, but 2 and 3 are already in the graph. We need to check if adding this edge creates a cycle. We do this by calling the DFS function. Okay, so we call the DFS function 2, 3. Okay. First, we check if current is equal to target here. Current is equal to 2 and target is equal to 3, so they're not equal. We add 2 to the visited set. Okay, so we add 2 to visited. Okay, if DFS, now we iterate over the neighbors of 2. The neighbors are 1. We move to the neighbor 1 and call DFS graph 1, 3 visited. Inside DFS for 1, we call 1, 3 visited. First, we check current is equal to target. Here, current is equal to 1 and target is equal to 3, so they are not equal. Okay. Move the neighbor to 2, but 2 already has been visited, so we skip it. We move the neighbor to 3 and call DFS 3, 3 visited. Okay, inside DFS for 3, we call DFS graph 3, 3 visited. Now current is equal to target, both are 3, so we return true. Since we found a path 2 to 3, the DFS call will return true as well, and the DFS call for 2 will also return true. At this point, we know that adding the edge 2, 3 would create a cycle, so we return this edge as the redundant one. Okay, interesting. It's a good way to solve it. Would I have thought about that? No. But it has been a good day, you know. I felt like we made a lot of progress in the graph problems. A little bit with recursion as well. So, yeah, I'll see you guys tomorrow. Appreciate you guys watching.